I'm a fan of simulation software, not a developer. I use the software, and I'm grateful to Dr. James Shippen in Coventry University in England for providing some of the software. I'm going to show you some beautiful simulations of what happens when people move. So by way of background, again, we're talking about the knee and the force magnitudes between the tibia and femur. And for knee replacement, various arthroscopies, I think it's important to know those magnitudes. And so we're going to try to show you a little bit about what I've learned through some simulations. The force predictions from a simulation are not always reliable, and that's probably an understatement. We're using simulations, at least I use them, to help me understand just what the questions are and kind of make hypotheses. So the predictions themselves are only as good as the inputs that you have to the simulation or model that you're using for the system. And what this is governed by is the assumptions you need to make. And the way these simulations work is mostly you try to record movement while people are moving and then work backward to find out, well, what forces could have caused those using such equations like F equals ma. What forces caused those motions? And that's called inverse dynamics, working backwards. There are some estimations of the forces that are involved that come from such things as a ground force plate, and lately from actual endoprostheses that are implanted in the hip to get some real information on what forces are being applied to the joints. And even more recently now, people are putting sensors inside the artificial knee to record the in vivo forces. But this is the major kind of error that we have, or the uncertainty we have in the simulation, is what actually are the forces involved in correlation. So just as by way of disclaimer, the predictions that we're going to see are based on some assumptions. The major obstacle then is there's limited in vivo measurements of muscle and joint forces. These are we're trying to make better measurements, and part of my talk at the end will be to show our work where we're trying to provide an estimate of these in vivo forces. And I'd like to point out Dr. James Shippen's at Coventry University, who provided some of the software we worked with. So the knee, during stair climbing, these surgical outcomes, clearly I think physicians and surgeons know they're affected by what the tibiofemoral loading environment is going to be. And of course, stair climbing is a classical and traditional way to say, well, what kind of forces would the average client be subject to? And these forces come from the direct bone-to-bone contact and as well as shear between the tibia and femur. And I think Dr. Lee showed some really good simulations of those happening. I think one of his simulations showing both condyles, the fact that he could actually simulate the forces not just as a flat joint but more complex geometry was really a very excellent contribution. But the forces also come from muscles as well as the ligaments. So I know very little about the knee. It's complex to me. It's more than a hinged joint. But when I begin to simulate it, I realize, well, there are the ground reaction forces that then have a reactive force somewhere, up above, and these things to be stable must, there's vectors must sum to be equal to 0. But as you can see that there's going to be a torque when you have these kind of muscle pairs to tend to flex the knee. And so to respond to that, the muscles must need to compensate for that. And in this case, the quads need to provide an extensive torque. And they actually increase the contact force of the muscle. So every time your muscles contract, you're actually adding to the compressive contact force of the joint. And this is especially true of the knee, especially when you're trying to, climb up on a stair where you need actually that musculature to pull you up. And so what kind of body forces are in play over here? And in fact, there is each year, I don't know for how many years it's been going on, it's called a grand challenge competition of measuring these, or trying to predict these in vivo loads. And there's been some in vivo data sets available freely for competitors to try to predict these contact and muscle forces that are being experienced. So a lot of the data are from force measuring tibial prostheses in amputees, which you would think would be ideal sort of data where you have a totally artificial leg, and now you can put your best sensors in that prosthesis and measure the direct force, and we'd get a good idea. So these are, however, they're models because the artificial knee is never anatomically even closely correct to the real human knee. So I'm going to show you, well, here's a radiograph of one of these prostheses with the actual strain gauge placed in line with the tibia, so that it theoretically should give you a very good record dynamically of people moving about and measuring these forces. Here's some snapshots of what we're going to be looking at, which is a leg beginning to rise from one step and then up to a higher step. And the data that we have from this study, whose publication is shown there, showed that there are significant increases over the body weight in terms of the shear force and the vertical force when a person climbs up a stair. And these are people that have a hip endoprosthesis, so they're not jumping upstairs, they're moving probably slower than the average. But the shear is doubled. The anterior-posterior direction, the shear is doubled as the stairs climb. And the amount of force, of course, is related to the flexion. Anything beyond 15 degrees drastically increases the force. And the vertical force goes up to anywhere 5 to 7 times body weight during the step. And of course, the speed of the step, which relates to the frequency spectrum of the loads, also vastly impacts the actual force. And so here's some data from that same study. So during walking, you see maybe a few times body weight, kind of a biphasic peak, and just looking at the vertical force. And then a stair climbing, it goes up to 6 or 7 times body weight. But the key thing to note is that in studying 7 or 8 patients, the inter-patient or inter-individual variance was very high, as well as the intra-individual during stair climbing is high. So it's kind of important to know when you're dealing with the post-surgical outcome what kind of forces are going to be experienced here. So what I'd like to show now is some simulations of the walking motion that we did by modifying the software. And again, the way these simulations were derived were by taking individuals and using 12 cameras, at least 12 cameras, recording the motion very carefully. And so one of the inputs to the model is extremely accurate and good. That's from the cameras. The other inputs, in terms of trying to measure what the forces are, estimating them, is variable and probably not as reliable, nearly as reliable. So here is a simulation of the step, a relatively slow stair step, where we're now looking at the individual and just looking at the muscular activity mainly in the right leg, which is doing the step, and actually showing the quad, the muscle force in the rectus femoris. The good thing about this model is that you can visualize it in different planes, however you'd like to show it. And some things I have not shown here is you can actually pick out a single joint. If I wanted to pick out the knee, I would just click on that and it would be amplified and you could see what's going on. And the muscular forces are color-coded according to, from green to red, according to their activity level. And you can see what happens here is that the force, which appears as an arrow, implies that the person is now stepping up on the stair, and then the stair is ascended. So the way we modeled this was just by simulating that force of the body weight. And what we see is that the muscle force goes up to 1,200, 1,250 newtons peak, and gradually, or rather sharply, declines. I just want to point out, I don't know how credible this actual waveform is. Having looked at Dr. Lee's simulation, I'm a little more of a believer. His looks somewhat similar to what he was showing. And so we're not really so much interested in whether or not this is a terribly accurate simulation. However, it does give us some idea that during this particular simulation, we can record the muscle force of individual muscles. And this program allows you to select, if I wanted to select the vasti, for instance, or the hamstrings, which are working against this, I could do that by clicks of the mouse. So what we can then do is say, well, what is the net joint force with the same simulation? And here again, he's standing there with two arrows. Finally, this one foot leaves the ground. There's a large arrow indicating his left foot is taking the load. And then when he reaches the step, his leg is now free. Pretty soon he's going to reach the step, and the large force is applied. He's moving himself up, and the quads are doing a lot of the work. And you see that it's going up to about 6,000 newtons peak. And the way we've entered the body mass of this individual, that works out to be about, I believe, about 7 times the body weight. You can actually compare different muscles. And this is one of the things of the quirks, you might say, of simulation here, is that there are too many muscles and not enough equations to figure out what the exact force from each muscle is doing. So it's actually a redundancy problem. There's too many muscles when you figure all the muscles of the quads plus the hamstrings and various other muscles. So you need to go through an optimization procedure, and what you do is you assume certain forces that are applied by the muscles and then work back with an assumption. And that assumption usually is that the nervous system is smart enough to continually evaluate a cost function. And that cost is how much torque am I using? What is my total sum torque to make a given movement? And the assumption is that the body or the nervous system, perhaps like some of us, tries to be as lazy as possible and wants to minimize those forces and those torques. And so that's the assumption that is used in order to calculate these various muscular forces. Now, as I said before, the speed at which you are moving and applying force, of course, drastically affects the forces. And here we have a quicker stair step, which produces a almost double size peak in the force, going up to, according to this simulation, almost 15 times the body weight. Whether or not that is accurate, really, probably, I don't believe anyone has the data to verify that. But nevertheless, we can see both the total knee force at the joint as well as the muscular forces used to lift the joint as well as stabilize it. So what are the accuracy of these loading predictions? Well, there's these mathematical models that use these assumptions that I've been talking about, the optimization and the cost function, that indicate peak forces anywhere from 4 to 9 times the body weight. And these are variations that actually occur using the same data. So what we're talking about is the models themselves are highly dependent on the assumptions that are used. So really we need to look at what the inputs to these models are in order to really find out whether or not they're reliable. There are very few models that actually use the muscle activation directly to predict the force. And this is a topic I'm going to take up at this moment here. There is no proven non-invasive method for measuring muscle force. But animal studies have shown that there are large forces that are passive, completely undetectable or invisible to the EMG, the standard method. And these are due to really the winding up or the stretching of our musculo-fascicular tendinous complex as we move. And these forces then are used to move the joints kind of as a freebie. There's no muscular activity required because it's stored in the springs of the system. So the EMG, even if you had the EMG for these predictions, wouldn't be very good because they only measure really the very surface of the muscles, and is depending on how deep your muscles are, you're missing a very large portion of the force that would be moving these joints. So I want to present some of our results now on surface muscle pressure, which we have tried to estimate some of the muscle forces. And here, just comparing surface muscle pressure over here with these sensors with simultaneous EMG on the quads, and putting them on the same leg and then having subjects walk. And we ran 10 subjects with this study, showing on one leg we had both the surface muscle force as well as EMG, and another leg we had just the EMG. Just looking at isometric contraction, you see in blue the EMG, which is typically noisy. In fact, EMG is Gaussian noise from all the neuromuscular activation. And the force of at the surface, which really resembles, you might say, a low-pass filtered version of the EMG, but yet reflects it quite closely in terms of time. And looking at gait cycles, let's say about 3 complete gait cycles here, we see the EMG, which is typically, we see in the quads, a burst of EMG activity as close to the heel strike where the knee needs to be stabilized. Very little activity afterwards. So each step you find that activity. Radically different is the surface muscle pressure where you see two peaks, a large muscle peak near beginning at the onset and followed by a fairly large one right near where the swing begins to extend the muscle, extend the knee. And here's another picture showing several superimposed EMG records during a single gait cycle, heel strike to heel strike. And we see the surface muscle pressure with this peculiar sort of morphology. And you compare that morphology with the actual flexion angle of the knee, and you'll see that the peak, the second peak here corresponds with a time when the knee is really ready to begin a major flexion just prior to swinging forward. And so the question is, well, is this, how artifactual is this? Is there any credibility to the fact that this represents the actual force of the quads? So again, a simulation helped us believe a little bit more, although we're still a hypothesis, that this is using sim software, that during the gait you have the normal electrical activation of the muscle, which is to stabilize the knee. But then as the knee is beginning to flex and wind up the muscle, you're going to generate a large force then that is able to, just like a rubber band when it's wound up, is able then to propel the muscle. So there's sort of circumstantial evidence that we can look at this biphasic force then as a actual estimation of the real muscle force non-invasively. So I just want to show and talk about finally what a little bit about this software, which was written in MATLAB. I guess it's a little jerky because I had to reduce the size of the file. And there are 133 muscles that can be represented here. Dr. Shippen actually works in a lab that studies injuries due to dancing, and so this is actually a dancer. One of the good things about the software is that since it's in Simulink, users like myself can come in and say, well, I want to manipulate this joint angle and I want to look at these muscles, and you can apply whatever loads you want. So I'm hoping that very soon the software will be available. So I'd like to conclude then that simulation, at least for me, things that I can't calculate, I can simulate, and they help us formulate the right questions, really form hypotheses. And there are a lot of people working on some hard data that will help improve the accuracy. And so we have seen some simulations of the quads during stair climbing, and Dr. Shippen, I'd like to thank the MathWorks, and I believe that the young students I've had working on this probably will be superior to any of my efforts, at least with playing with computer programs, because they're much more familiar with it. And I'd like to thank Todd Alter, Colin Kozinski, Alex Kransner, and Manoush Moratti for helping me with this with these simulations.